Here is Svetlana and Ivan.
Okay, so hi guys, my name is Svetlana. I'm a PhD student in Moscow State University. My co-speaker is Ivan. He is a master student in the same university as well. So today we're going to present our work on shellcode detection for ARM-based devices. Actually, for ARM-based platform. So first of all, we'll briefly discuss why it's still actual. After that, we'll briefly discuss the main difference between two platforms, x86 and ARM, because nowadays it's well known that we have a lot of shellcodes detection algorithms, approaches which based for catching shellcodes for x86 platform. And our research is mainly focused on is those methods applicable to ARM-based platform, and how difference between two platforms can possibly impact the structure of shellcode and some other features of shellcodes. And what can we learn from it? So let's start. Now we know that amount of ARM-based devices increasing significantly. We know that it's already boosted in times devices on x86 platform. For example, it's our cell phones, it's our tablets, it's network devices, a lot of routers and controllers, even for SDN platform, SDN networks work on ARM-based devices. It's already laptops, for example, we know about Chromebook and so on. We still have a huge base of code written in C and C++, those codes that we want to inherit from other systems. We want to reuse it somehow, it contains a lot of vulnerabilities, and we're talking about memory corruption vulnerabilities. They're still there. Well, every time I speak about those problems, shellcode detection problem, with people who are interested in virus detection and so on, I'm hearing one simple question. Is this problem decidable at all? Because payload could possibly have a huge variation of what it can do. So how it's possible to detect it? The answer is that we exploiting some certain vulnerabilities, like it's memory corruption vulnerabilities. So we want to override some pointers, and that leads to some structure limitation and size limitation inside our shellcodes. So we will focus on that. That's a simple example of shellcodes which focus on stack overflow. So typically, such shellcodes have activator which can be presented by an obsolete or some kind of get PC code which trying to understand its own location on the others. On the other space of executable process. So as we want to evade from detectors like signature-based detectors, even behavior-based detectors, so we want to obfuscate our code somehow, that's why we typically have decryptors there. So payload and return address zone. Well, the other question, maybe it's not that bad at all, because since we know about this problem, if I remember everything correctly, more than for 20 years already. So we have a lot of protecting techniques like stack canaries, self-SAH, DEP, ISLR, and so on. So probably we don't have problem at all, but unfortunately it all were bypassed. So again, back to our problem. We have, as I mentioned before, so we have a huge base of detectors which focused on detecting shellcodes on x86. What we have for ARM platform. So we have already seen shellcodes. So they already exist in public repositories such exploitdb or Metasploit database of exploits and so on. But unfortunately, we don't have shellcode detection methods that will be at least a little bit smarter than like simple signature-based. So what we're going to do with it? So first of all, as I mentioned before, we want to understand how two platforms differ from each other. Of course, it's two absolutely different platforms, and the number of differences is huge, but we want to focus on those that can possibly impact how shellcode looks like. So let's briefly discuss it. So first of all, the common size in ARM platform is fixed. In x86, instruction size varies from 1 byte to 16. Actually, in ARM-based platform, we have 32 bits for ARM CPU mode and 16 bits for SAMP mode. And actually, it's fixed. So it's lead to such techniques as self-synchronizing disassembly. So in x86, it doesn't matter from which byte of set we start to disassemble our code. We will certainly have some point at which we will synchronize our disassembly. It will helps us to detect shellcode because it will be doesn't matter on each offset, but we can probably miss some significant instruction. So there is possibilities that we don't understand that we cached shellcode or something bad. So as I mentioned before, again, we have two different CPU modes. So there is possibility to switch between them dynamically. So what in shellcodes that we have already analyzed, I mean for ARM platform, we have already seen this obfuscation. So, for example, you trying to disassemble your shellcode, your piece of data to ARM mode. So you have some signature on it. So you try to detect those signatures. If you will switch to another CPU mode dynamically, so you will break your signature. So it's like a simple obfuscation technique. So another interesting stuff that there is possibility of conditional instruction execution. So in ARM platform, we have several group of instruction, and some of them can be executed or not executed. It strictly depends on the flag values. So speaking about, for example, rope shellcode, when you trying to construct your malicious payload from legitimate binaries, from piece of libraries and so on. So here we're not speaking about rope, but it's some kind of same probably high-level idea. So imagine totally legitimate executable. So if you construct your executable from conditional instructions, so you can have your malicious payload from innocent executable by just by varying flag values. So to be honest, we haven't seen such shellcodes yet, but probably we'll see them in future because, again, for me it's really interesting. Okay, in x86 platform, we to have an access to program counter, we have to have some kind of get PC code. Again, here in ARM, we don't have to do it because there is possibility of direct access to it. Okay. In ARM, we have load store architecture, so it isn't possible to access memory directly from arithmetic instruction. And the other stuff that function arguments and return address also go to registers and not to stack. So, like naive question. So, what we can do with shellcodes? Because how we can run it because it's not in stack and so on. Well, actually in ARM we have such features that if we have some embedded functions, every second and others function return address zone goes to stack. So it's totally executable, definitely, I mean. So here is a simple example. of conditional execution. So first of all, conditional execution was used in embedded system. So it was used for compactization of programs because it was critical. Embedded system, size limitation and memory limitation is really critical. So, but again, as I mentioned before, it's really cool technique for obfuscation. Here is example of SAMP CPU mod and ARM CPU mod. It's the same piece of code, so we can see that in some mod we can again compress our binaries and we have some free space to do everything else. Well, again, so we analyzed all shellcode detection techniques which are used to detection of shellcodes for x86 platform, and here's like local recap. So static analysis is really difficult. Static analysis, I mean, which we used for detection of x86 shellcodes, because it's for example some analysis of control flow graph, instruction flow graphs, data anomalous as well. So it's really difficult in case, for example, of conditional executions to construct such control flow graph. It's very time consuming, so it's not reasonable to use it here. Well, and dynamic analysis, much more difficult. Well, I've mentioned it before, okay. So, and what's the next step? So we already have an ongoing research on detection of shellcode for x86 platform. So basically how we did it, we identified set of features which are typical for shellcodes. I mean features, not features of payload, it's not signature based, it's specifically behavior based, and it's trying to analyze some specific type of obfuscation which typically used by shellcode writers. Well, for now we want to understand are those features applicable to ARM-based platform, and can we identify something new? So here is the list of static features, and okay.
Here's the list of shellcode features that which could mark the shellcode in the incoming traffic. Half of these features came from x86 shellcodes, and the remaining ones are the IRM shellcode features. So we will run through this list of features and then check them on the examples of real shellcodes. The first feature is correct disassembling of data. The point is that the shellcode is executable program, so it has continuous chain of instructions. If you would like to disassemble random data in chain of instructions, with a high probability this chain will not have particularly big length. So, starting from a certain threshold, we can assure that we see a shellcode. The second feature is one related to the shellcodes for IRM. This feature represents the technique of writing IRM shellcodes. More than 80% of existing IRM shellcodes uses this technique, so it's a good feature. Another one tells that shellcode is trying to find its location in memory. This feature is changed x86 shellcode feature that is called getPCCode. The difference is that we check not only an access to information about location, but also check how shellcode use this information in his functioning. Then, two ones are features of programs which correctly forms system calls or library calls. Every shellcode is an executable program, so he needs to make system calls with right arguments, so we can use this as a detection characteristic. Another one tells that shellcode contains the decrypt routine. Of course, shellcode can be encrypted, and he requires some functions to decrypt it and redirect the control flow to the shellcode payload. Next feature is the return address zone, which contains valid addresses. We can check the incoming flow for these valid addresses. And the remaining ones are normal conditions for every shellcode. Okay, let's consider a few examples. The first and the simplest feature is the length of disassembled chain. With the help of this feature, we can distinguish random data from the executable code. here we see that the shellcode and random data, and then they were disassembled to a chain of instructions. Seems like shellcode will be longer than random data. So, if we want to detect a shellcode, we should check that the length of instruction chain is bigger than some threshold. But interesting remark appears. IRM code has a huge density, so random data could be disassembled in a long chain too. How can we find necessary threshold? The answer is that the shellcode is surrounded by random data, and this data increase the length of disassembled chain of this shellcode. So it's not a problem to find proper threshold. The second feature. This is the most interesting feature, I think. This feature tells that shellcode use a change to thumb mode. What's the point here? More than 80% of the IRM shellcodes in the web were created with this technique. So, what is this technique? Shellcodes are written in thumb mode, and at the beginning of the code, there is a selector to thumb mode. For the change in CPU mode, we need to make a jump to the address of thumb code, and the last bit of the address should be set into 1. In IRM architecture, code is length by 4 bytes, so we can use the last bit of address as information bit. Okay, let's take a look at the example. Here is the shellcode that you can download from exploitable.com. At the beginning of the shellcode, we have the prefix, which takes the address of thumb code with writing it to A6 register and adding with 1, which is thumb mode number. Next instruction is branch instruction, which makes the switch between CPU modes and jumps to the thumb code. This technique is used for making shellcode smaller or to providing more functionality in the same size of the buffer. Because the length of IRM instructions is 4 bytes and thumb instruction is 2 bytes, so the code is far more compact. That's why more than 80% of the shellcodes have been created in this way. But if the attacker is not burdened with the size of shellcode, he can go further. He can use this technique for obfuscation. One can divide the code into small parts and write every part in some processor mode that is different for preceding part of the code. So, if we try to disassemble data from every offset, every instruction chain will be small, because instruction for one processor mode may not be disassembled in correct instruction for another processor mode. But the attacker still needs to produce switching between these modes. So, every disassembled chain should contain the switch routine. Thus, we may check instruction chains for these routines. The next feature, get use PC code. In x86, get PC code was a normal feature because there is no direct access to program counter register. So, we used different methods to get it. For example, we could call function and then gather the return address from the stack. This method gives us a certain fingerprint in the control flow graph, which can be detected with control flow graph analyzers. Unfortunately, in IRM, we can directly get program counter register without any redirections. That is to say, the existence of get PC code could not be the strict property for the detection. So, we updated get PC feature to get and use PC feature. Okay, what is this feature? This feature tells that there was an access to value of program counter register, and then this value was used in load, store, or jump instructions. Let's take a look on the example. Here is the shellcode decryptor from exploitable.com. The first instruction puts the address of the last decryptor's instruction to A6. Then, this value used to make a jump to the BL instruction. Here is the pattern we need. Then, value of program counter is written to the link register with the use of BL instruction, because BL is a function call, and the return address puts in LR register. So, LR points to the encrypted shellcode. This value used 3 times to get another encrypted word, to put the decrypted word back, and to jump to the start of decrypted shellcode payload. How do we define get_use_pc code? We define it by running an abstract execution. We forward the instructions, but don't make operations on the registers. But every register has two Boolean values. The first value means that this register has been initialized by concrete value. For example, if we put constant in R0 register, it becomes initialized. The second value shows that this register is somehow indirectly referred to the place of shellcode in memory. How we define it? If there were the operations that put program counter to the register, this register started to point to the address of some part of the shellcode, and the second Boolean value becomes true. Then, if we make operations at this register, and if all arguments of these operations are initialized registers or constants, the register remains indirectly addressing on the shellcode on the stack. Otherwise, this register becomes uninitialized. Next feature is the existence of correctly formed system calls or library calls. This means that arguments of these calls should be initialized. Let's consider the part of the ARM shellcode from Metasploit framework. Here we can see some system calls. How we use system calls in ARM? All registers from R0 to R6 used for arguments for system call. And R7 register keeps the number of the system call. To understand that we've got a correct system call, we need to check that some arguments have been initialized and the R7 register has been initialized too. If we wouldn't check for this and only check the existence of system call, the precision of our detector would be critically small, because there is a big probability to disassemble a system call somewhere in random data. This call is only 4-byte value. So, even if we have a lot of these system call bytes, this should not be interpreted as a shellcode. Seems that our feature already works twice. As we can see here, calls socket, connect, and there will be more following. The existence of read-write cycle. This feature tells that decryptor routine should have a cycle that conveys load and store instructions. Because this routine should load encrypted payload from memory, decrypt it, and put it back. Let's consider the shellcode decryptor from exploitable.com again. In R4, we put the count of the cycle, and with the use of the R14, we write the shellcode where the shellcode will be executed. In this instruction, we had put the value of the program counter register, so it refers to the shellcode. We see there is a cycle, and it covers two instructions: load and store. Okay, but we make some limitations on this feature. All registers that are used in load and store instructions should be initialized. So we have to use the same abstract execution technique that we have seen previously. If there was no such a limitation, it would be more than 50% of false positive rate. Because sometimes the random data has cycles that convey a lot of data that may contain load and store instructions. But if these registers were initialized, only then we will be able to mark the decryptor. Another interesting feature is the existence of return address zone. The return address zone is a range of valid values of addresses. These addresses should be valid because they redirect the control flow to the shellcode. So, this address zone should allow the execution of instructions. Otherwise, we will get an access violation. On the example, we see how the shellcode overflows the buffer to write this return address. So, if we check the data for these valid address zones, we can detect shellcode. This is a very simple technique. Okay, almost all features that we reviewed earlier have their mapping to the dynamic detectors. The dynamic detectors are identified in the virtual environment. We run an emulator and then run the shellcode in the emulator to identify these features. we can analyze malicious system calls, using of program counter register, switching to different processor modes with the emulator. It will have more accuracy, but it also will have more complexity. Trying to combine the pluses of static and dynamic detectors, we come to the idea of hybrid classifier that will be explained a bit later. Now, let's consider a few features that can be examined only in dynamic analysis. The read and write from memory, which marks the decryptor. We run a shellcode and we see that he did the n number of reads and he also did the n number of writes. You may assume that this is a shellcode which has read some payload, decrypted it, and put it back on the stack. Therefore, to understand that we've got a decryptor routine, we should count the number of memory reads and writes and compare them with the threshold value. There is a very important point. We count the number of the unique memory reads and writes. I mean, the number of memory cells where reads and writes were done. If we didn't do that, there may be random data which has an endless cycle which writes only one byte in the same place. By all indications, this is not a decryptor. Another decryptor feature is providing control flow to the shellcode payload. After decryption, the routine should make a jump to the start of decrypted shellcode. Thus, we need to check that there was a jump to the addresses where the writes were done before. And we also take into account that number of these writes should exceed the write number threshold. But this could not be only a jump. It could be every arithmetic instruction, because we can directly move the address to the program counter register. Luckily, we run this in the emulator, so we need to check only that the value of PC register is equal to address where the writes were done before. Here is an important example why the dynamic methods get complicated in the IRM architecture. IRM architecture provides conditional execution. This means that instructions can be executed or ignored depending on the flag register value. This provides by the conditional suffix in the instruction. For example, we have two emulations of one program with different entry conditions. At first, there is a block of the instructions with the AL suffix, providing that this instruction will be executed with all flagged register values. So, it seems that this block will be executed in both emulations. Then, we have add instruction with the not equal suffix. That means that this instruction will be executed only when zero flag set in 1. So, the instruction will be executed only in second emulation. There we see the S suffix. This means that this instruction can change the flags register value. So, in the second emulations, flags become 0 and 1. Then we have the CS block. It works when carry flag set to 1. After this block, there is an E block with instructions that executes only when zero flag set to 0. This block changes the R3 and R4 registers. So, the next add CCS instruction that executes in both emulations gives different result. I mean, the same instruction in the same place gives the different result in different emulations. This example means that we can't know what initial values of the flags register use at start of the emulation. So, we should emulate the same code 15 times, because we have 15 conditions in the IRM architecture. And if we want to use only the dynamic detectors, we should emulate the same code from every offset, because shellcode can be anywhere in the analyzed data. And that affects the performance of detection. So, if we want to wisely use all these features together, we should make the hybrid classifier.
So, Probably there is a question why we stopped so in depth in such simple heuristics. Of course, we don't want to throw away all research methods and research approaches which were done on shellcode detections. Basically, we want to combine them in some optimal classifier, but that heuristics that we mentioned before, they provide a good distinguish between legitimate flow. So what I mean? So we implemented all these features as some shellcode detection library. So each and every vertex in that graph means that it is some classifier of some specific feature of shellcode. So if some vertex said that it's probably shellcode, we would transfer it to the others one. So the main idea here is to put the simplest detectors on the top of topology. So that helps us to reduce legitimate flow as fast as possible and to analyze with dynamic methods or with existing shellcode detection methods, which works, which are sometimes time-consuming on the top of topology and run it on the most probable shellcode. So this works like a decision-making tree. After that, all information collected on decision-making model, which says that it's possible shellcode, and moreover, it classifies shellcode. So by classifying shellcode, I mean that we are able to say that this shellcode is shellcode because it has, for example, an obsolete. This shellcode, we believe that this piece of data is shellcode because it has some certain type of obfuscation, and so on. As I mentioned before, our previous work were focused on shellcode detection for x86 platform. So we implemented it as open source shellcode detection tool called Dimorphos. Here we extended it for a model which works with shellcode for ARM. So our experiments was on 4 data sets. It was shellcodes which were collected from public repositories and like exploitable or Metasploit as well. So we were also testing on legitimate binaries because all existing shellcode detection methods doesn't work really good on legitimate binaries. They have a lot of false positives. So it was also random data, like collected normal traffic of normal user working on the system, and multimedia as well. Again, it was lead. We collect multimedia because shellcode detection algorithm, which exists right now, works really bad on multimedia. Our experiments shown on the current slide. This is results on throughput. Again, we used simple laptop with a virtual machine and its characteristics mentioned on the bottom of the slide. So, I'm sorry.
Hi. Excuse the interruption. We have a tradition, a new tradition. You like that, right? So no, you're part of the tradition. Come back over here. So this young lady is a new speaker. What do we do with new speakers? That was really lame. What do we do with new speakers? There you go.
Give me one of those too.
So you're doing shouts.
Yes.
So we need one more. Give that to him.
Fuck off! Oh, shit. Wow, that is... pretty sure they just heard me on the moon. That is seriously mic'd up, boy.
How about some love for the new speakers?
L'chaim.
Caution, testing progress.
It's the bottom of the barrel.
Oh, wow. Holy shit, that smells.
That was sweet.
Checked in.
What?
You can go back about your business.
So it's much more funny now, you know. So experiments.
Okay.
No, man, I'm cool for tonight.
Actually, he drinks for the first time.
Oh, yes. For the test purposes, we produced a vulnerable application for Android smartphone. The version of Android is 2.3.3. The vulnerability is a simple buffer overflow, and it hides in the dynamic C library that is loaded through the Java native interface to our application. We wrote the exploit for this vulnerability with Metasploit and used the shell bin TCP as a payload. Okay. Okay, we adjust the parameters of the exploit, and just a second. Here. No. And here we made the Dimorphos tool to listen the incoming and outgoing traffic. Okay, let's start the exploit. Here we see the Dimorphos tool found the shellcode in outgoing traffic for this IP address and TCP port pair.
So again, it works surprisingly well on the simple heuristics, but again, as I mentioned before, we use sophisticated algorithms which run on obfuscated shellcodes. So thank you guys for your attention. Thanks for being on the very last time slot on the very last talk. So we really appreciate it. Well, where is question slide? As far as I can understand, Q&A section will be on the lobby or as a whole. Yeah. Mm-hmm. Okay, so we still have 7 minutes. If anyone have questions, so we be happy to help you. Okay, thank you.